All right, so what we'll do tonight is to continue the discussion of instructions. And tonight we'll talk about two instructions that are kind of important. I would say really, really important. Your lab is going to handle two instructions. So your lab is going to handle the instructions called LD, ST, and LDI. Those are basically instructions to copy or move content, copy content into registers or out of registers. But tonight's focus is going to be on the instructions, conditional branch instructions, as well as the compare instructions. So those two are really important because together they basically form, the mechanism by which we can have control structures in assembly language. Okay. So for the most part, I don't need Canvas anymore. I just need to run Logisim to show you guys, how all that stuff is done. So we'll go ahead and start Logisim, Java-jar, and is it in? Yep, this is in the root folder. All right. So I'm going to load up the processor first. And there were also a few questions of, at this point, since I do not have quote-unquote notes or modules anymore, so how do we take notes? How do we learn all this stuff? There was a comment on the Monday-Wednesday class, that I'm going a little bit too fast and people did not have enough time to write down what is important. So if that is the case, okay, if you're writing down something and I'm already moving forward and talk about something else, just raise your hand and ask me and say, okay, I need a little bit more time to write down, the concepts. That's perfectly fine. It's not a problem. Is that okay? All right. So, or if you have any questions, like if any part of my explanation is not clicking, raise your hand and let me know which part is not clicking. Because at this point, everything kind of stacks up. In other words, all the new concepts depend on the older concepts. So if you have a gap somewhere, it's gonna impact the understanding of the newer concepts. So it is particularly important at this point to make sure that we do not move forward unless all the concepts are clear. All right. So here's the processor. I'm just increasing the screen intensity on my side because otherwise I can't see it. Oh, actually I can look at the big monitor too. I can use either one. All right. So the first thing we'll do is we'll go ahead and write a simple program that makes use of compare and a conditional branch instruction. And I can do that using just a plain text editor. So by doing this, I'm kind of showing you the tool chain, and how to utilize the tool chain over and over again. So the first instruction is the Cmp instruction, and we can compare two registers. This particular architecture can only compare registers to register. It cannot compare against constants. So if you want to compare to a constant like 1, you have to load the constant 1 into a register first using the LDI instruction. Then you can compare against that particular initialized register. So I'm just going to randomly pick register B and register C. So compare BC, okay, if you want to understand what it's going to do, we'll go to the opcode table and also the assembler manual to understand what it's going to do. And then the next instruction is going to be choose a flag. Okay, we have 5 flags that you can choose from. We have the carry flag, which is also known as the borrow flag. We have the Z flag, which checks for 0. We have the sign flag, the overflow flag, and also the L flag, which checks for less than in the case of signed interpretation. Pick one. You guys get to pick. Which one do you want to use? Which one do you want me to illustrate in this case? C? Okay. So we use the carry flag to a particular label. So this I here implies that this is jump with immediate, which means you can actually specify a label after the jump instruction. So for the lack of meaning, with this label, we'll just call it label L1. And then we have a halt instruction here. And then at label L1, we have another halt instruction. So this is a very, very simple program where it will perform a comparison, and then based on the result of the comparison, Sometimes it will go to label L1 and stop at the second halt instruction. Other times it will not perform the branch to L1 and it will continue execution with the first halt instruction. If I were to comment this particular program, I would basically say, at this point, it is saying if the carry flag is a 1, then we have a simple go-to statement in C and C++ to label L1. And in this case, the C flag is basically set if and only if B is less than C as unsigned numbers. So if I really want to emphasize what it's doing, it is basically casting B and C to unsigned, do the comparison, and C is non-zero if and only if B is less than C as unsigned values. So is that helping? Kind of illustrating what the assembly instruction is actually doing, and using the equivalent code in C, C++. Yes?
Like you just said, we cannot just compare the registers raw without them actually having something in them. So right before the compare, you would then essentially put
that is correct.
in B and then put something in
Yep.
C.
So they are uninitialized to begin with. So that means before I track down the behavior of this code, I'm going to inject values into register B and register C because I don't want to do some constant loading in here. Then I have to change the source code and then run it again. But using this, I can always just change the values in B and C, reset the simulation, and then start over again. Yep.
And then in the comment for compare, the leading C is a capital. Is that supposed to be a separate value, or is it?
You mean, okay, so this one is referring to register C, and that's why it's lowercase. This one is referring to the flag C. So if you want it to be absolutely clear, you can just say this is the C flag or the carry flag. And then this B is basically referring to register B, and this C is referring to register C. Yep. I can see how it can be a little bit confusing because we have a register C, but we also have a flag, carry flag, which is also represented by C. So is that more clear? Because I have to change the other one to also to indicate this is the C flag or the carry flag. Is that okay? All right. So the first thing is, if you don't have the assembler, can we figure out the opcode of all of these things by ourselves? Okay, that's the first question. The second one is, what is a label? So the label, like this one, this is a label definition. A label itself can be a name that is anything that an identifier can be in C and C++. So if you just think about the name of a variable in C and C++, anything that is legal as a variable name, you can use as the name of a label in this assembler. So L1 in uppercase L, is just one example. Okay, you can use lowercase as well, but it's case sensitive. If you use uppercase, you have to continue to use uppercase. It is case sensitive. So this label definition is basically saying L1 is now the symbolic name of whatever is right next to it. In other words, in this case, L1 is the symbolic name of the halt instruction. It is not, L1 is not the halt instruction itself. It is not the opcode. It is the symbolic name of the address of that halt instruction in RAM. Are we doing okay so far? More or less. Okay. Okay, so we'll go ahead and look up the opcode table, and then we'll try to hand assemble all of this code by before we feed it through the assembler. Yep.
For the second line with Jci L1, that would be distinct from like L1 colon, right? Like you could potentially have like a different label that was L1 colon.
L1.
With a colon after.
This is not the place to define L1, so you cannot have a colon here.
Yeah, but I noticed when I use the assembler, if I accidentally put a colon there, it doesn't error out. So are you able to use like L1 colon as a label?
Yeah. Oh, I did not know that. Okay.
Or is that like a problem?
That was not intentional.
Well, will it still jump to the right label?
I do not know. If it reports it as an error, that means it's not working correctly. But if it does not report as an error, then it depends on how it defines label L1 with a colon as a name of a label.
I might it, just not see the
Oh, okay.
Not notice it.
Okay. All right. So we'll go to the opcodes table in the shared folder, and I just cleared out, all the folder stuff, so I have to go back to the shared folder from here. Here we go. And I want to go to the share folder itself. There we go. And then we go to processor and opcode table. Now you guys are more than welcome to copy this, all of these documents into your own Google Drive. So this way you can comment and annotate your own copy, and you can bring a printout of your own copy to the next exam. Okay. So the first instruction is a Cmp instruction. So we are trying to look for Cmp. Okay. P is right here, and let me just magnify a little bit. It's just every single time I have to do it like that. There we go. So Cmp doesn't do much. All it does is to perform a subtraction. It doesn't even store the difference back into one of the operands. Okay, so x and y are both unaffected by this instruction, but the compare or the subtraction operation does go through. So that means the only side effect that we can observe with this instruction is the flags getting changed. The carry flag can get changed, the 0 flag can get changed, all 5 flags can get changed by this particular instruction. Is that okay? And then when you look at the bit pattern, it is 1110, which is E in hexadecimal, and then it has a pattern of XX, Y, Y. XX is representing the 2 bits to represent register quote-unquote X, which is the minuend, and then Y is the subtrahend. So in our case, we want B as X, so that would be 0, 1, and then we want C as Y, that would be 1, 0. So that means the actual bit pattern of this opcode is 1110, 0110. In hexadecimal, that would be E6, because 0110 is 6 in hexadecimal. Is that okay? All right. So switching back to here, okay, I'm just going to add to the comment here and say this is 0x6c, EC. E is 1110. Oh, this is 6, by the way. Okay, I got both wrong. 6 is 0110. So that would represent that we are subtracting C from B, but we are not storing the result. The next instruction is a Jci instruction. So we'll go to the table and look up Jci. Okay, and I think Jci is one of the earlier ones. That's JC, and Jci is in the earlier part here. So Jci I, okay, the first I is a part of the mnemonic itself, and then the second I is representing an immediate operand, which can be a number, can also be a label, which is a symbolic name. So in this case, the opcode is 44, because 0100 is 4. So we have 44 and then followed by the actual definition of whatever the label is. So if I switch back to the code here, so we have 0x44, and then we have whatever label L1 is. So from the assembler's perspective, at this point, it doesn't know what L1 is, because the definition of L1 is after the reference. But that's okay, it will resolve it eventually. Okay, so I'm just putting L1 here as a tag to myself and say that, okay, we need to fix this later. And then the next line is a halt instruction. We know what a halt instruction is. The halt instruction has an opcode of 01. So we have 0x01. And now we have a label definition of L1. So now the question is, what do you think the symbolic name L1 is defined as? In other words, we're trying to do something, it's kind of to the effect of this. Pound define L1 to be something. So if this program or this code is at the beginning of the entire RAM, then the E6 is going to have the first location, which is known as location 0 or address 0. This is address 1, this is address 2, this is address 3. So whatever is L1 is going to be at location 4. Okay, so this is actually the same as location 4. And that's why, at this time, I can go back here and say, oh, this is just location 4. And then the halt instruction is right after this, at location 4. So that would be a 0x01 as well. So the code, the opcodes of this particular program is E6, 44, 04, 01, and 01. The label definition itself does not use up any RAM location because it's really just saying, oh, whatever is following this label definition, that location now has a symbolic name of L1. Yep.
So, okay, so sorry, I'm trying to think about like how to.
No.
So
Give me-
labels don't exist in the assembly language itself. They only exist in the assembler.
It does not.
It's just an abstraction that the assembler provides.
Yes.
Okay, that makes sense.
It's a shorthand to make your programming easier, but it is not a part of the output of an assembler.
Right. Okay. So it. Okay. Yeah.
That is absolutely correct. Any other questions? Yep.
What is the reason we need the second halt?
The second halt, so that we can differentiate whether we branched or not.
So we can replace the second halt with other commands, and then it would say that if GCI L1, so if C flag 1, then it would go to the other commands and run what's below the first halt.
Because I want to be able to differentiate where I went.
Yeah, what we're saying is that if C flag is 1, jump to address 4, which is defined by the label, and then compiled, assembled into the binary output, and then it's saying run everything below the starting at
So we
address
need
4.
it because we're using the jump?
Yeah.
Yes, because we are testing the jump instruction, and I want to be very clear whether the jump happened or not.
To continue on to his question, would we be able to change? Would we be able to move L1 up and then remove the second halt, and then just have it jump to halt, like we would go to.
But then you won't be able to tell whether it fell through
yeah.
or whether you actually jumped to that instruction.
But it's possible to do that. There's nothing.
Yeah, there's nothing syntactically, there's nothing wrong with it, but then
It just makes no sense.
but then the code does not serve the purpose that it's supposed to serve anymore.
Okay.
Yep.
So after the Jci instruction, there's whatever like actual constant value the assembler put there for whatever L1 like refers to.
Right. So internally, what the assembler does is it keeps track of the current current location that is not filled yet. That is no one is using it just yet. So at the very beginning of the assembler, that counter would be at location 0, and then it encounters the compare instruction. And then the assembler says, oh, I know how to figure out the opcode of this thing, and then it goes to location 0. But once location 0 is used, then the next available location is going to be 01. And then the assembler look at the second line and go like, oh, it's a Jci instruction, I know how to assemble this, but this one takes up 2 bytes because the opcode takes up 1 byte, and then there's another byte that it will use up to represent L1, so it takes up 2 bytes. So now we have used a location 0, 1, and 2. And the next available location is going to be location 3, and at location 3 we have a halt instruction. So the first halt instruction is going to be, it has an opcode of 01, but it's going to location 03 in RAM. And then at that time, okay, location 03 is used up, so the next available location is 04. Then it sees the label definition of L1 : and as a result, L1 : is now defined to the next available location, which is 04. And then after that label definition, the assembler sees the second halt instruction, and it goes like, oh, I know how to assemble the halt instruction. It has an opcode of 01, and it's going to take up the next available location, which is 04.
So in memory for JCI would be the output for JCI and then 04.
Say that one more time?
In memory for the JCI instruction would be the output for JCI and then 04.
That is correct. So that's why we have 44, which is the opcode of JCI, and then we have the 04, which is the immediate operand of the JCI instruction.
So if we're just trying to find like what address of instruction ends up at RAM, we just ignore the labels because they don't change any of that, right?
That is correct. Label is a convenience feature. In other words, if I were to write this program by hand, if the label is really just a placeholder, so that I can remember to go back and fix that location and go like, oh, okay, that is actually at location da da da.
So that's kind of what I was saying, is that like it's not an instruction set. So the processor itself has no concept of what a label is at all. It's an abstraction that's created by the assembler that basically says within the assembler, for every time that you see L1, replace it with the address that's here. So it's just an abstraction created by the assembler. So if you were to write this out by hand, you wouldn't worry about defining L1 at all. You would just count out manually what address you were looking to move to, and then you would just replace everywhere that you wanted L1 with that address. But
which is very tedious.
Very tedious. Yeah.
And that's why we like the assembler.
Yeah. Thank you for giving us this.
Yep.
I understand we're keeping this real basic, but if we're using this as like a if then else type of idea, is there a way to get out of the then? So if we actually drop into the first halt, that was an actual instruction.
You can use a Cmp instruction, which is unconditional to branch to wherever you want it to go. So you can branch around the else branch to the continuation, whatever is after the conditional statement. So we'll get to that. We'll definitely get to that part probably in a week or so, because I need to go over the basic instructions first, and then we'll look at how to structure the basic instructions to implement control structures in C and C++. So we will go over, okay, this is a conditional statement. The matching assembly code looks like this. This is a for loop. The matching instructions look like this. What if you have a for loop inside a conditional statement? Well, you just nest the structures. Okay, so those are all very good questions. Yes?
Does it have to have the first halt statement?
Say that one more time.
Couldn't it work without the first halt?
Without the first halt instruction, I would not be able to differentiate whether we performed the conditional branch to L1 or not. Because if we don't perform the conditional branch instruction, it will just continue execution with whatever is next to it. But then without the first halt instruction, it's going to continue with that single halt instruction anyway, so we would not be able to tell whether we did a branch or we just continued execution without a branch. So that's why we have two halt instructions here. So is that okay, or any additional questions? No additional questions. All right. So I'm just do a Control-C, Control-A, Control-C, go to the Assembler tab. I don't have it open yet. Okay, so we'll open it. Go to the source and Control-V. So they're pasting into it. And you can see that in the other class I was doing something similar, not exactly the same. So now we have the code pasted. It did not generate any errors. And when we go to the assemble output, you can see how the code generated is matching the addresses that we talked about. So at location 0, we have E6. At location 1, we have the bytes 44 and 04. At location 3, we have 01, which is our first halt instruction. At location 4, we have our second halt instruction, which is also a 01. So is that okay so far? Because this is kind of important, that we can hand assemble a program, and then this is just double checking to make sure that I did not make a mistake in the process. If you scroll a little bit to the left, you can also see how the labels are defined, because this is label L1, and you can see how label L1 is defined to be 4 at this point. So that is kind of the cool part of it. And I lied because labels are actually case insensitive. It converts everything to lowercase first. So I lied. I forgot about the script. Yep.
I just wanted to double check on the columns. W is like where it will end up in RAM, and X and Y are the actual outputs for X would be the output.
Correct. Yep. So column W is telling you the address of the first byte on that row, and then column X is the first byte of that row, but optionally you might have a second byte on the row as well, so that's why we have column Y. Okay. So are there any questions about this part of the assembly process, the assembling process? Yep.
So there can really only be 2 bytes on a single line?
Yes, but that's only because all of the instructions that we have implemented up to this point only take up to 2 bytes. So there's no need to worry about things that have 3 bytes because we do not have any constructs that is a 3-byte construct. All right, so the RAM file tab is convenient because now instead of hand copying everything from here to the RAM component inside the simulator, we can just go to File and then we say Download As, and then go to Comma Separated Values or CSV. And I changed my browser, so now it actually asks me what name I want to save it as. So this is a Jci Instruction test program. I just call it jci.csv. Press the Enter key. It is saved. So now we focus on the simulator itself. It's always a good idea to reset the simulator first before you run anything, just in case the registers are already initialized to something. So just type a Control R. There's one little downside of pressing just this reset button, because pressing that reset button, you can reset all the registers, but it doesn't reset the clock itself. So if the clock is, if you leave it last time as a high, pressing the reset button here does not change the clock back to a low. So that is the problem of just using the reset button here. When you type Control R, the clock is automatically reset back to a low. I can demonstrate that. So I can change the clock to a high, and then I type Control R on the keyboard, and you can see how the clock is reset back to 0. So that's a much more reliable way to reset simulation.
Oh, you would the other way, just turn the clock and then click the reset.
Say that one more time?
Turn the clock to high.
Yeah.
And then click the reset.
It doesn't change it. So that's why Control R is the more reliable way to do it.
I just want to see it.
Ah, yeah, okay. So now we can load image from the temp folder. It is called jci.csv. Open the file. Now we have the content here. So I could just zip through the whole thing, execute the whole thing at full speed, but that would kind of defeat the whole purpose of this demonstration, because the conditional branch instruction is implemented in a kind of interesting way. Okay. So I want to go through this whole exercise, actually going through the instructions one by one. So my first question is, how do we want to initialize register B and register C? Do you want to see it branch, or do you want to see it not branch? That's the question. We'll do one and then do the other one, so it's just a matter of ordering.
Might as well do the not branch first then.
Do the not branch first? Okay, so in order to do the not branch, the default is not going to branch, right? Because when you subtract 0 from 0, will the borrow flag be set if you're just subtracting 0 from 0? Okay, so that will definitely should cause it not to branch. Okay, so that's fine. So we'll go with this. All right. So at this point, I don't need to go through the details of the fetch or the decode. We can just, we can kind of zip through those two and then go straight to the execute cycle. So we have Control T, and now we have the execute cycle. And you can see at the execute cycle, the address of ROM is basically the opcode with a 0 padded to the right-hand side. We explained that one as well, I think, in the previous class, because that has to do with how we pad a 0 using this particular merger. So I'm not going to explain that anymore. So now our question is, okay, what is this doing? Okay, and before we explain that in LogicSim, it is also helpful to look at how the opcode is explained in the documentation. So you can see how JCII is explained as if C is non-zero, then we copy whatever the program counter has to the program counter itself. If the carry flag is a 0, then we increment the program counter by 1.
Isn't the first one compare?
Oh yeah, we are comparing first. Okay, sorry. Okay, so we'll do the compare first. So the compare instruction is using the ALU, and you can see how the enable of the ALU is a 1, so that means we are about to use the ALU. So this this part of the explanation is something that I hope you will find useful, because when I ask you, okay, if I give you a brand new instruction and it has no mnemonic, I just give you the long 7-digit hexadecimal digit, and I ask you to figure out, okay, what does it do? Okay, so how do you analyze the processor to figure that out? So the first thing you do is to ask which components are active. Okay, so you look at the EN. And the order is not that important because you can go forward or backwards. So in this case, the ALU is active, and when the ALU is active, when you look into the ALU, when it is active, some operation is going to perform, because you can see how the enable. Let's see. Yeah, so you can see how the ALU enable pin is used to enable the demultiplexers, these two demultiplexers. It is also used to enable the multiplexer. And then there's a second part that is also really useful. It is called the Scl Pin. This selects what operation do we want to perform in the ALU. The ALU is capable of performing, let me count here. It is capable of performing one of 6 operations. It can add, it can subtract, it can right shift, it can do a bitwise NOT, it can do a bitwise AND, it can also do a bitwise OR. So now the question is, which one do we want to do? Because the selection is 0, 0, 1, so that means the demultiplexer is going to the second operation, which is the subtraction. The other demultiplexer is going here, and then the result of the subtraction is the one that is being get through to the multiplexer to the output. Okay. But when you are performing a subtraction, then the question is, what are we subtracting? Who is the minuend? Who is the subtrahend? How do we get those values into the subtractor? So now the question is to track down what is connected to in1 as a pin, what is connected to in2 as a pin. Okay, so now we have to zoom out, and then we track down these 2 wires. Where is this connected to? Where is this connected to? So you have to do it one by one. This one is connected to the output of this particular demultiplexer. So now the question is, are we selecting, is the demultiplexer itself enabled? And the answer is yes. Okay, you can see how RO0EN is enabled. So that means the demultiplexer is in fact enabled. The second question is, are we selecting the right output? So you click on this wire, it is 0, 1. This is 0, 0, this is 0, 1, so it is in fact selecting the right output. And then the input to this demultiplexer is coming straight from here, which is the output 0 port of the register bank. So now we go into the register bank, and we say, okay, who is feeding to output 0? Is that okay? Are you guys still following me? Okay. That is controlled by register output 0 select, and it has a 0, 1 at this point. So that means input 0, 1 becomes the output. This is input 0, 0. This is input 0, 1, which connects to register B. So this is how we figure out that register B is connecting to in1 of the ALU. Is that okay? The process is tedious, okay? But it is not undoable, because each component is not too complicated. It is the interconnection that seems overwhelming. So now we try to track down in2. In2 is coming from this particular multiplexer. The select bit of this multiplexer is a 0, which means input 0 is connected to the output. So now we track down this wire, which is the output of this particular demultiplexer. The demultiplexer has a selection of 1, which is okay, that's exactly what we want. But the input of this demultiplexer is coming in from out 1 from the register bank. So once again, we have to right click on the register bank and say, okay, who is feeding to this output pin? So we look at register output 1 select. It is 1, 0. So now we track down, this is input 0, 0. This is input 0, 1. This is input 1, 0. That is connected to register C. So now we know that register C of the register bank is what is feeding into in2 of the ALU. So are we still doing okay so far with all of this tracking? So zooming back out again, now we know we are subtracting B, register B from register, excuse me, we are subtracting register C from register B. B is the minuend, C is the subtrahend. Okay? So, but the ALU also has multiple outputs. The first output is here, it is the result of the subtraction. Now that's not surprising, 0 minus 0 is 0. So the next question is, are we doing anything about this particular output? That output is here, it's already presented on this wire. Are we doing anything about it? Yep, go ahead.
Right before this, so in the ALU, the N1 and N2 just references which register is feeding the data into them.
Correct. According to the way we set up all the multiplexers and demultiplexers, yes. So register B is going to in1, register C is going to in2. Okay? So this output from the ALU is connected to the input of this particular multiplexer, and the multiplexer is not enabled. So that means, hey, you know, we don't have to worry, we can stop at this point. Because the input is not connected to the output, so it doesn't really matter what happens after that. Okay. But there's one more output from the ALU. It is called the flags out, which is the output of the flags. So it has a value of 0, 2 at this point. Okay? So why do we have a value of 0, 2? And what is this flags out thing? So we do a right click on the ALU, and you can always track it in both directions. You can start with the pin itself and then go backwards. So the pin itself is right here. It is the flags out port of the ALU. So now you look at this wire, and it is a little bit complicated because this wire is the output of this particular splitter, and now you can track on each individual one and go like, okay, why is it reporting 0, 1, 0, 0, 0, reading from the least significant side. Okay, so we'll track this down one by one. Okay, the first one, or bit 0, is C out. Okay, so now you want to look at okay, what is C out? C out is right here. It is the output of this particular multiplexer. This multiplexer is using the same select as the overall ALU, which is 001. This is 000. This is 001, which is connected by a tunnel called B. So now you track down this tunnel B, and that turns out to be the borrow, the borrow output of the subtractor. In other words, the C out, or the bit 0 of flag out, the flag output port, is the borrow output of the subtractor. Is that okay? All right. What about the next one? What about the Z flag, right? So this is the next one. So where is Z out defined? Z out is defined out here, okay? And how is that defined? It is the result of a NOR gate applied to every single bit of the result of the computation. Which means if at least one bit of the result of a computation is non-zero, then Z out is going to be a 0. If all the bits of the output are zeros, then Z out is going to be a 1. That's the only time it's going to be a 1. So in short, the Z flag is a 1 if and only if the result of the computation is a 0. Is that okay? And that's why it is a bright green right now, because 0 minus 0 turns out to be 0, and that's why the Z flag is a 1. What about the next one? The next one is called the sign flag. The sign flag is easy. The sign flag is just bit 7 right here. You can see how this wire connects to a very strange splitter. That splitter splits only paying attention to bit 7, which is the most significant bit, and that becomes S out, or sign out. So the sign out is just the sign of the output of the entire operation. All right, the next one here is the overflow, okay? So the overflow is O out, and O out is defined up here. This is O out. And you can also see that O out is the output of the multiplexer. This multiplexer is using the same selection as everything else. This is input 0, 0, 0. This is input 0, 0, 1, which is the one that is currently selected. So this circuitry is what we are using to compute the overflow flag. Okay? So when you look at this circuitry, you may or may not recognize it, because the last time we saw this, it was in the form of an expression, but this is really the same expression. But you might want to track down, okay, so now we know what S out is because we just talked about it. Okay, that's the sign of the result of the operation. So in this case, it is the sign of the difference. So now the question is, okay, what is S1 and S2? So once again, you highlight those things, and then you track it down. S1 is defined out here. It is the most significant bit of in1. S2, on the other hand, is the most significant bit of in2. In1 and in2. In other words, S1 is the most significant bit of the minuend. S2 is the most significant bit of the subtrahend. And you can now see how we use the most significant bits of the minuend, subtrahend, and the difference in order to compute the overflow flag. So that's how we track down everything in order to understand what a particular operation is how a particular operation is performed. In this case, this is what compare is going to do. Now that we know how flags out is computed, is it going to be stored somewhere? Because the output of stuff usually is going to be stored somewhere. And in this case, flags out is connected to the input of this register here. This register is called flags, and it does have the enable turned on, which means in the next rising edge, the flags register is going to remember the bits coming out of the ALU, which means the result after a compare is actually remembered by a register. In this case, it's called the flags register. Is that okay? All right. So let's go ahead and have a rising clock, and you can see how the flags register is now updated to 02, which means bit 1 of the flags register is now a 1. Everything else are zeros. Okay, so that concludes the execution of the subtraction instruction. So the moment I have a control T again, which is a falling edge, the microcode pointer will go from E60 to E61. E61 is 2 followed by all zeros, which means it's going to reset the microcode pointer back to 00, which means we're going to be ready to fetch the next instruction, which is going to be the fun one, because that's our Jci instruction. So control T, you can see how it goes back to location 000, and now we're going to fetch the opcode 44. So we do another control T. You can see how the instruction register is now 44, and that 44 is going to become 440 to put into the microcode pointer, because that's the result of the decode operation. And then in the next transition, we'll be going to location 440, because that's the first location of the ROM to describe how to implement the instruction of JCI. So we have another transition, and you can see how now we are at location 440, which is the fun stuff. This is how the branch instruction, conditional branch instruction, is implemented. Do we have any questions at this point? I just want to give you guys plenty of opportunities to copy stuff if you want to, or ask questions if you do have any questions.
We are recording.
I believe so, yes. If not anything else, we are recording the cricket.
Give it up for the cricket, everyone.
Yep. Yep.
So, in RAM, we have our instruction 4.4.
Yes.
And we send it to ROM as an address. Does that mean that the command itself is already in ROM?
Yes. So the opcode that you put in RAM, so the RAM only consists of opcodes. The opcode is what you can write as a software engineer or as a programmer. The stuff that is in a ROM typically is inaccessible to a programmer, and that is really just a part of the processor that you cannot change. You can look at the opcode in RAM kind of like a subroutine call. Okay, it's just saying, oh, we want to compare, and it's encoded in a very compact way. But exactly how do we compare? We have all of these multiplexers, demultiplexers, registers, and so on and so forth. How do we connect these pathways, and what do we do in what sequence? That you cannot see from 4.4 as the opcode itself, but when you get to the ROM, the microcode ROM, these are called microcode slices. Each location in ROM, I call that a microcode slice because it is representing at that particular slice of time, how do we make connections between the components inside the processor. So that in return is the actual implementation of the instruction that is represented by opcode in RAM. So in a way, what we stored in ROM is kind of like a definition of subroutines, whereas the opcode that you store in RAM is really just a function call. It's just like, oh, do this. But how do we do it? Well, that's defined in the subroutine, which is basically what we have in the ROM. Is that helping the understanding? Okay.
Thank you.
Mm-hmm.
So for like the pattern of what you went through, you were mainly concerned with like, okay, I'm gonna step up to compare, check what's enabled. I know it's gonna do an X minus Y, so the ALU should be enabled. You look at the ALU and you trace from the input to the output. The output's not out yet, so you step a little bit.
Yep.
From the output.
Yep. And you can start with any component, because but the idea is you want to make sure that everything that is enabled is analyzed. So if something is disabled, you can just kind of not kind of ignore that. But if anything is enabled, you want to analyze what's going into it and where it is going, where the output of that component is going.
Do you usually have to step a couple times to get the output, or is the output usually like right there?
All the instructions at this point are single ROM slice instructions. So that means it only really takes one single rising edge to finish the entire thing. All right. So we are now at location 440 in the ROM, which means now we are setting up all the connections between the components to get the Jci instruction working. So let's go ahead and check what is active and what is not active. Okay. And typically, what you want to focus on are the registers. So you can see the register bank itself is completely inactive. Input enable is not active. Register output 0 enable is not active. There's no way to quote unquote disable register output 1, but you can also see that there's nothing going on here. The ALU is also inactive because the enable is dark green, it is a 0, so the ALU itself is not active. The flags register is quote unquote inactive, which means it is not going to be updated. But whatever content it has, it keeps outputting. So the output of the flags register is always outputting its own content. Okay, so you have to keep that in mind. Registers always output. So the only thing that is active, based on what we can see in on this particular screen, is the program counter itself. The program counter itself has its enable being a 1, so that means we know in the next rising edge, the program counter will be updated. So now the question is, how are we going to update it? Okay, so that question only has one single answer. We track down what is connected to the D port of the register. Okay, so that would be this wire. This wire is coming out of a multiplexer. So now we analyze the multiplexer. The multiplexer is controlled or selected by PC mux. So now we want to say, okay, so who's PC mux? Unlike PCEN or PC enable, program counter enable, PC mux does not come straight from the ROM. Okay, it is actually quote unquote computed somewhere else in the processor. It is not a bit pattern that is specified by the ROM. So you want to track that down, and it is the result here. Okay, so let me scroll a little bit over. So you can see PC mux is actually the output of this multiplexer, and that multiplexer by itself is controlled by a title called PC mux mux. It is the multiplexer to a multiplexer. Okay. Funny name. This one does come from the ROM, which means there's no you cannot it's not calculated, it's not computed. So when you click on this one, it is 0, 0, 0, which means we are taking input 0, 0, 0, which is this one, as the output of this multiplexer. That is why PC mux is a 0, because input 0 of this multiplexer is a 0. So now we track down this wire and go like, okay, where is that coming from? It's coming from the output of the flags register. In other words, when you track this down, okay, it is coming from the flags register. It's bit 0 of the flags register. So from the outside, it's kind of difficult to remember which bit is which flag. So before you can actually remember, that you have to go back into the ALU and then look at the ordering of the flag register flags out. So you can see how input 0 here is corresponding to the carry flag. In other words, from the outside, we are now checking out what is the carry flag. And the carry flag turns out to be 0. And that's why PC mux is getting a 0. So now getting back to the program counter. So the program counter is right here. So PC mux being a 0 means input 0 is used to update the program counter. That turns out to be the output of the adder. The adder does have a input carry in as a 1, so we are in fact adding 1 to the program counter. Now, the next question is, why are we adding 1 to the program counter? Where do you think the program counter is pointing to right now at this point? Okay, I will give you 3 choices. Is it pointing to the opcode of the Jci instruction? Is it pointing to the immediate operand of the Jci opcode? Or is it pointing to the instruction that is next following the PCI opcode? So A, B, or C?
B.
B is correct. Okay, who said B? Okay, good job. So B is correct. So right now the program counter, which has a value of 0, 2, is pointing to the immediate operand of the Jci instruction itself. Okay, if you don't believe me, we'll go to the assembler and double check. So when you go to the assembler, the assemble tab is particularly helpful. So you can see how the Jci L1 instruction is starting at location 0, 1. So location 0, 1 is corresponding to the content of 4, 4, which is the opcode of the Jci instruction. But the byte right after that is a 0, 4, which is L1. So the program counter is now pointing to the 0, 4 at this point. If I do not do the increment of the program counter, the next fetch cycle is going to fetch this 0, 4 and attempt to decode it and execute it. That is not correct. That is not the intention of this 0, 4. Whether it is a valid opcode or not is irrelevant, because it is not intended as opcode. It is intended as the operand to the Jci instruction. Is that okay? So this is why we have to increment the program counter so that it skips this location, because we are not branching. This 0, 4 location has no use. And then we have to branch, we have to increment the program counter. So the next byte that it points to is the 0, 1, which is corresponding to the halt instruction after the Jci instruction. This is why it is not branching and just continuing to the next or whatever instruction is following. So are we doing okay so far with the analysis of the Jci instruction when it is not branching? Yes, sort of.
Needs time to sink.
Okay, so we'll have some. I'll give you some time to soak it in. And do you want to go back to the processor screen? Yep. Mm-hmm.
So it's the Jci, and then after that, it's currently pointing at what the label was referring to, like the thing after that label, right? But the way the actual compare ended up, it's forcing it to jump right or to increment the program counter one more time.
Right. Yep. because the only choice here is really PC mux. So PC mux is really the key to the decision-making process. Should I just increment, or should I get it from somewhere? Should I get the new value of the program counter just by adding one to whatever it has now, or should I get it from the other side of this multiplexer, which comes from somewhere else?
So if it worked out the other way, we would actually get a number in on the mux that would be changing the program counter instead.
Yes, which we will also demonstrate, but but at this point we're only demonstrating when in the case that it is not branching. When the carry flag is at 0, it is not branching, and this is how it continues execution to whatever is next to it. Is that okay? Are there any questions? Yeah, go ahead.
So it's pretty much just skipping a line, like skipping the line code?
It is not really skipping a line. It is just ignoring a part of this particular instruction that is not of any use because we are not branching.
Okay.
So instead of consuming it and making use of it, we're just saying, we don't need it because we're not branching.
Oh, so it sees it, but just says that. You can just like basically throws it out. Like,
Say that?
It's basically kind of like well, it doesn't throw it out, but yeah.
Yeah, it's just ignoring, but it has to skip it because if we don't skip it, then it will try to execute 04 as if it is an opcode. But that's not the intention of that 04.
I think.
Mm-hmm. Yep.
So it couldn't do something and then overwrite it?
Overwrite what?
The instruction?
Well, the Jci instruction does not overwrite anything. It just reads from memory location. But at this point, we're not even concerned about that part. We're just saying, oh, okay, we're just incrementing because carry is a 0.
Couldn't you say JCI to 0001 and then use the first location?
Are you referring to the assemble tab like this one?
Yeah.
What about it?
Instead of using 4, because we used 4.
Okay, which 4? Are you talking about this 4?
Yeah.
So instead of using 04?
What if you use 01?
Then the conditional branch will try to go back to itself if the carry flag is a 1. Which means if the carry flag is a 1, you have an infinite loop because there's no way to get out of it. Okay. Any other questions regarding the conditional branch instruction when it is not branching? No questions? Now, this is something that you can do as well, okay? Because the analysis of this circuit is really nothing more than looking at the multiplexers, demultiplexers, the registers, and so on. And you already know how each component works. Now it is just a combination of, okay, so how do we analyze this whole thing? The other thing that you can kind of keep in mind, which is handy, is at this point, the processor is static. In other words, it's not doing anything, okay? It is the transition of the clock that's gonna cause it to do something. So you can analyze this entire picture in a static way, and it's okay because all the components are basically not doing anything. They're all static at this point. Is that okay? Sort of? Okay, all right. So we'll have a rising edge right now. So when I do Control T, we'll have the next clock transition. Since the clock is low at this point, the next transition is going to be a rising edge. So that means the program counter should go from 02 to 03, like that. And that concludes the execution of the Jci instruction. And then when I have a falling edge, the microcode pointer will go from ROM location 440 to 441. And 441, as you will probably expect, is 2 followed by 6 zeros, which means we're going to reset the microcode pointer back to location 000 to begin the next fetch cycle, which is the fetch cycle of the halt instruction. And we kind of know what the halt instruction is going to do anyway, so that's not going to be, a whole lot of fun. Is that okay so far? Okay. All right, so if that part is okay, we just want to confirm that we're going back to location 000, and we are loading the halt instruction into the instruction register, and then we'll decode it to location 010, at which point we're going to be stuck. Okay, there's no way to get out of this one. Okay, all right. So if that part is okay, we're going to reset the entire processor. Control R resets the whole processor, and we'll reload the content of the program in. And this is the nice part of having it saved in the file, because you can just reload it when you need to. Okay, but this time we'll set up the register where a carry would actually happen. Okay, a borrow in this case. So yeah, pretty easy to do. That will do it, right? Because we are looking at B minus C. Subtracting 1 from 0 will definitely trigger a borrow. Is that okay? So we'll do it this way this time. Go back to main, and then we observe the microcode pointer. So Control T, it is this is the first instruction. This is the compare instruction. So we'll go ahead and execute the compare instruction, just like that. And then we want to look at the flags register and say, oh, why is it 15 now? Okay, why is it 15? What does it mean when it's 15? So the explanation is going into the ALU itself, and then you go all the way down to here. Yep, go ahead.
So I noticed that the counter goes from 1 to E6. Why specifically E6?
Because the opcode itself is E6. We pad a 0 to the right hand side.
Okay.
And then that becomes the new address.
So it's dependent on what the opcode is. So if we change, so the initial Ucode pointer will change depending on what you're passing into it. Okay.
So the way you look at it is each opcode in RAM has up to 16 lines of wrong locations to implement.
Okay, that makes sense.
So you have basically pages. Each page has 16 lines.
Yeah.
But because the address is only counting in lines, so if you want to turn to a particular page, you want to multiply the page number by 16 to get to the first location on that page.
Yeah. Okay, that makes sense. Yeah, sorry, I was.
No, that's good. It's all. Yep, it's good to reinforce those concepts. Yep.
This processor can't store variables besides the 4 registers that you would have stuff like that.
It can store into RAM, which is where the variables are going to be, quote unquote variables are going to be.
Oh, okay.
Variables are stored in RAM. Whether you're dealing with assembly programming or whether you're dealing with C programming, they're all stored in RAM. It's just that at this point we are not quite ready to talk about variables and how to store into variables yet.
Oh, so now, for now we're just referring to them.
Yeah, for now we are
Being
focusing
all
on.
the registers.
Yeah, we are focusing on just registers and the control structure at this point. Okay, so getting back to the flag register, why is it 1, 5? Well, that part is actually easy. This is the 1 because you can kind of imagine it has 0, 0, 0 ahead of it. This is the 1, so we have 1. 0, 1, 0, 1 is 5, and that's why we see 1, 5 as the content of the flag register. So that part is easy. But now the question is, how come the carry flag is set? Well, the carry flag is set because it is connected to borrow, and the borrow is connected to the borrow out of the subtractor. 0 minus 1 triggers a borrow because you're trying to subtract more than you have, so the borrow is going to be a 1. So that explains why C out is a 1. What about Z out? Okay, Z out once again is the exclusive OR of all the bits of the output. Okay, so when you have 0 minus 1 or 0, 0, 0, 0, 0, 0, 0, 0, minus 0, 0, 0, 0, 0, 0, 0, 1, what do you get? You get 1, 1, 1, 1, 1, 1, 1, 1. So just to be super redundant, what is the OR of 8 ones? 1 or 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 1 is 1. Good. What is the negation of that? 0. Okay, good. So that means, now we can explain why the 0 flag is a 0, which means the result is non-zero. What about the sign flag? Well, the most significant bit of 1, 1, 1, 1, 1, 1, 1, 1 is a 1, so that's why the sign flag is a 1. And then the overflow flag is a 0. That's because of the computation that is occurring right here, and that gives us a 0. The sign flag does make sense, okay? And then the exclusive OR between the sign flag and the overflow flag is a 1, and that's how we define the L flag. So the L flag says, yes, 0 is in fact less than 1, even if you interpret it as signed numbers. Okay, so that's why the flag register is the way it is. But to us, the most important part is the carry flag is a 1. Question?
Yeah, I was just curious why there's the 2 overflow structures.
One is for one for addition and one for subtraction. They are different.
Oh, I see.
Yeah, so when you're doing addition, you are looking for the same sign for the 2 numbers, and then if the result is a different sign, then you have a problem. When you're doing subtraction, then you're looking for the subtrahend and the difference to have the same sign, but they're different from the minuend, then you have a problem. So that's why they're different. Okay. So are we good so far with the result of the subtraction mechanism? Okay. So we zoom out again, and just to double check, okay, we can also look at the output of the ALU, which is this wire here, and indeed it is FF or 1111 1111, but it is not going to any place that makes a difference. In other words, it is being ignored. Okay. So now we go back and forward, continue with the next instruction. So Control T, we go back to the fetch cycle. This time we're fetching 44 again, which is the Jci instruction or the Jci opcode. Okay, and then we go to location 440 as the actual microcode corresponding to the Jci instruction. And we already know what is going to be configured. We know that the program counter is going to be changed. But this time PCMux is a 1, and we kind of know why it is a 1 too, because PCMux is the result of this multiplexer. This multiplexer, just like last time, is still selecting 0, 0, 0 to become the output. But 0, 0, 0, or input 0, is corresponding to the carry flag. We kind of saw how we computed the carry to be a 1 in the previous in the previous instruction. So that's why PCMux is a 1. But when PCMux is a 1, it influences how the program counter is going to be updated. So let's go back to the program counter and see how PCMux influences how it's going to be updated. This is the program counter. This is the input to the program counter. This is the multiplexer to control what is going to be used to update the program counter. Yes?
So for PCMux, is that just always one of the flags, then PCMux just picks which flag?
Not always. So PCMux, the multiplexer that feeds to PCMux can also get the input from constants. So there are certain cases where we just say, no, it's going to be a 0, or no, it's going to be a 1. So there are cases where it is not conditional. Okay, but that's a good question. Okay, so now we're looking at the program counter, and we are saying, okay, now that PCMux is a 1, this multiplexer is going to select input 1 to become its output. Okay, so we track on this wire, which is the output of another multiplexer. This multiplexer is also having a select of 1, which means we want input 1 of this multiplexer and track down where it's going. So are we doing okay so far with this? Okay. Yep.
What did you physically change to input bytes 15? What did you load into RAM differently this time?
I did not change anything in RAM. I changed how I initialized the registers. I initialized register C to have a 1 instead of 0 like last time.
Okay. Thank you.
Yep. So in other words, we track down this wire first, and then based on the select bit of this multiplexer, we chase down this wire. Based on this particular select pin, we chase down this wire. So we look at this wire and go like, oh, it's going everywhere. Well, okay, so now the question is this the multiplexer doing anything? Nope, it is not enabled. And then we look at this Y here, okay, it's going to the instruction register, but it's going to the input of the instruction register, so it's not going to drive the wire in any way. And then we track it down up to here, go like, oh, okay, it is doing something with RAM. RAM selection is a 1, which means we are asking RAM to go like, okay, pay attention, we want you to do something. What we wanted to do is a read operation because the load port is a 1, so we are reading from RAM, which means whatever location you specify is going to be presented as the D port. It is driving. The D port of RAM is driving that wire. And right now it is addressing location 03, which has a content of 04. So that's why this 04 is eventually routed to the D port of the program counter, and as a result, it is used to update the program counter. Yes?
Isn't that location 02?
Huh?
Isn't that location 02?
This is location 02.
0, 1, 0, 2. I thought you said 03 location.
Oh, okay. 02 is correct. Sorry, I misspoke. Okay. But now the question, there's another question now, because every time you use RAM, you have to say, who is dictating the address? Who is telling me where we should be looking, right? So now you have to track down this wire and say, why are we looking at location 02? Who told us that? So that is the result of this multiplexer. It's the output of this multiplexer, which has a selection of 1, which means now we track down input 1 of this multiplexer, which interestingly is going back to the program counter. So that's why we're using the program counter to point to a location in RAM, and then we use the content of that RAM location to update the program counter itself. But we know that already, don't we? Because when you look at the opcode description, this is, okay, let me highlight which part I'm talking about. That tells you that when the carrier flag is a 1, we are dereferencing the program counter and then store whatever it's pointing to back to the program counter. But we see this as a C syntax, and then when we switch over to Logisim, we now see how it is implemented in circuitry. Is that okay? All right. So that means, you know, in the next rising edge, Control T, the program counter should jump from 02 to 04 because the input wire going into the program counter is 04 already. So not surprisingly, Control T, the program counter is now a 04. So when we conclude the execution of the conditional branch instruction, the next location that we're going to fetch from is at location 04. You can see that from here. It's another halt instruction, so when you look at the instruction register, you cannot really tell the difference. But when you look at the program counter, you know that it's actually using the second halt instruction, not the first one. And as a result, now we know that the branch actually happened because it is not going to location 3, it's going to location 4 now. So do we have any questions about this analysis? Okay, because the so-called studying for this class at this point is just tracking down how the instructions execute. Yep.
If we wanted to skip to a certain part of a program, is there any way to do that, or is it just step continually?
You want to fast forward to a certain place, but not conditionally. So you want to do an unconditional branch to some place.
Yeah, like.
Okay. So the way to do that, okay, let me.
Well, I meant like in the simulation for Logisim, like say we wanted to only look at like the very last halt, and we didn't want to really like step a ton to get there. Like, is there any way to make that faster, or would you just have to do it one by one?
You have to do it one by one. However, you can also use the log ability so that you just run it at full speed, but you log all the important stuff that is going on in between so that you know what's happening before you got there. So you can track it, you know, backwards. So that's a good question. Let me see if I have enough time to. No, okay. Well, the class time is actually over by now, but next time I can show you how to do that. by just writing a program that has a lot of loops. So it's going to take a lot of clock cycles to get through. But then we keep everything in a log file, so that this way we can analyze the log file to figure out what happened in during that time.
So I was thinking like if you do like break in GDE for like some random function way later on, you can just jump right to it.
It's not easy.
That makes sense.